let's learn about Earth's atmosphere. Now, most people I talk to seem to have the wrong idea about the atmosphere. They seem to think that it is significantly thick in comparison to the radius of the Earth, and it's simply not true. The atmosphere of the Earth is just amazingly thin. It's basically 500 kilometers thick, which compared to the radius of the Earth is nothing. It's just this very, very thin, gossamer veil of atoms that are held in place by gravitational pull of the Earth. So each atom in the atmosphere has a gravitational attraction to the Earth, and that's what holds it there. Now, the Earth, it has enough mass to hold them. If the Earth had less mass, it'd have less gravitational pull, and guess what? It wouldn't be able to hold an atmosphere, which is why the moon and asteroids don't have atmospheres. It's because they don't have enough gravitational pull to hold them. So the Earth is considerably larger than the moon. Remember, the moon is roughly about the size of the solid inner core of the Earth. It has basically 1/6 the gravitational pull of the Earth. So what happens is when sunlight hits the surface of the lunar surface, the atoms are capture that energy and they convert it to heat, so they move fast. So what happens is here's a gas molecule, and if it touches the lunar surface and it gets ejected upwards by this violently oscillating atom of the lunar surface, that molecule gets ejected away from the moon at speeds of maybe, let's say, 5-6 kilometers per second. Well, it turns out that's beyond what we call the escape velocity of the moon. Anything that leaves the lunar surface at more than 2.5 kilometers per second is not going to come back to the moon. It's just going to be launched upwards and never come back. If you push things away from the lunar surface at less than, say, 2.3 kilometers per second, they'll go up, slow down, and fall back down. But if you do it more than 2.5 kilometers per second, they go up and they just never come back. On Earth, it would have to be considerably higher than that, like 11.2 kilometers per hour. So it turns out that the temperature of the Earth is such that the atoms don't get pushed away fast enough to leave. So the Earth is able to hold on to its atmosphere. Smaller objects can't. Now, what is the atmosphere made out of? Well, it turns out it's not oxygen, as a lot of people think. It's almost all inert nitrogen. So, well, nitrogen isn't really inert, but it's mostly inert. It doesn't interact much with most things, as we saw when we talked about nitrogen fixation. Nitrogen comprises about 78% of the Earth's atmosphere, with most of the remaining being oxygen. And everything is like 1% is all the other gases. And of those, a lot of it is water vapor and argon. And notice this carbon dioxide is just a very, very trace amount. It's basically about 0.04% of the total atmosphere. This is going to be important later on when we talk about climate change. But let's go on and just talk about the atmosphere some more here. Okay, so atmospheric pressure is caused by the weight of all the atoms on top of you. So if you lay on the floor and I start putting sacks of rice on top of you, each time I put another rice bag on top of you, you feel more and more weight pushing down on you. It's the same thing. It's just gas atoms instead of bags of rice, and they're stacked 500 kilometers high, and they compress a bit. So what we find is that the pressure you feel at the surface of the Earth can measure different ways. So in the United States, they use pounds per square inch. So it's about 15 pounds per square inch. In say physics, we often use kilopascals. It's about 100 kilopascals. A lot of times in atmospheric sciences, we use what are called millibars, and so it's about 1,000 millibars, a little bit over. Okay. Now, what happens is as we go up, that pressure is going to get smaller because there's fewer atoms stacked on top of you. And it gets smaller at a nonlinear rate. And the reason is because of compaction. Atoms are a lot closer packed down below than they are up above. So as we go up, what we find is this. The pressure drops dramatically at first. So in the first 5 kilometers you go up from Earth's surface, you've already lost half the atoms. Half of the world's atmospheric particles are found in the lowest 5 kilometers. Now remember, it goes all the way up to 500 kilometers, but half of them are in the first 5 kilometers. And so what we see is there's this rapid diminishment of pressure. So 90% of all the atoms in the atmosphere are below 16, 17 kilometers up. And they gradually get less and less and less as we go up and up and up. Now, what else happens as we go up? Well, we find that we go through different layers They have different behaviors and different properties. So we only have one atmosphere, and it certainly isn't as thick as this shows. This is just blown up to give you a sense of. We have 5 different layers I need you to know about. And from the ground to outer space, they are the troposphere, which is where you and I live and breathe. Above that is the stratosphere. Above that is the mesosphere, followed by the thermosphere, which is also called the ionosphere, followed by the exosphere, which gives way to outer space. So at the top of the exosphere, the atoms are held so lightly that particles streaming off the sun hit them and they leave the Earth with an escape velocity and they never come back. Now, let's start with the different layers. The troposphere. The troposphere is where you and I live. It's the bottom layer. It's the one closest to the ground where the vast majority, 75% of all the air molecules are. It's where all the wind and weather is. It contains pretty much almost all the water vapor in the atmosphere. There's a little bit that gets up into the stratosphere, but not much. Uh, and one thing to note is that the temperature decreases with height. Now, this is called adiabatic cooling. It's something we'll talk quite a bit about. But within the troposphere, as we go up in altitude, we go down in temperature. So when we get to about, say, 10 kilometers or so, we've reached its coldest point, which is about a little below, a little close, fairly close to -60. And then what happens is we keep going higher, but the temperature quits changing. We've entered what's called the tropopause, which is the boundary between the layers. So the boundary between each of the layers, it has a suffix pause. Okay, so we have the troposphere and the tropopause. And you can tell the difference because altitude stops making a change in temperature. And then look what happens. The temperature starts going up when we get to the stratosphere. So the stratosphere, strata means layering, and the stratosphere contains layers of ozone particles. So the main thing to know about the stratosphere is this is where ozone is found. And I'm sure you've heard that ozone protects us from ultraviolet radiation from the sun. And basically what happens is in the stratosphere, light from the sun is converting oxygen into ozone and absorbing energy in the process. And that energy has to be expressed somehow. So it gets expressed as heat and potential energy in the ozone. But there's an increase in temperature, and since more of it happens at the top than the bottom, we get this heating over time. But first, I suppose I said this what's this thing called presentation to talk about how ultraviolet light converts oxygen into ozone. So here's what happens. Here's an O2 molecule, like what you breathe. Ultraviolet light from the sun hits it with enough energy to break the bonds, the double bonds between the oxygens. And so now I have 2 monatomic oxygen atoms that have been separated. So the energy in part was used to separate them. And what happens is they will then find another O2 and attach to it, releasing energy when they do, and forming O3. Now, this is a fairly unstable molecule, but it can wiggle in lots. It has lots of degrees of freedom, as we say. And now this one is able to absorb the next photon of ultraviolet light that hits it. Rather than breaking this just wiggles and jiggles and heats up. And for that reason, we find that this layer, instead of getting colder as we go up, it gets warmer as we go up. So in the stratosphere, we leave the tropopause, we find that the temperatures are getting hotter and hotter and hotter, and that's because these ozone molecules absorb ultraviolet light and convert it into heat. Then we reach the stratopause. So again, notice how the temperature dropped in the troposphere, stopped dropping with altitude at the tropopause. Then it began increasing as we went through the stratosphere. Then it stopped increasing when we reached the stratopause, and now it's going down again because we've entered the mesosphere. Now, the mesosphere is the least interesting of them, in my opinion. It basically all we can really say about it is very, very tenuous. It's very low pressure. 99.9 of all the molecules in the atmosphere are below it. So we're talking about from here up, there's only 0.1% of the atmosphere is left. And it's just the molecules are fairly far apart, and it just gets colder and colder and colder as we go up until we get to the mesopause. And there's not much happening in here, to be quite honest. Other than one thing to know is the coldest part of the atmosphere is the upper part of the mesosphere. Then here's what happens. We reach a mesopause. The temperature quits getting lower and it starts getting warm because we've entered what's called the thermosphere. Now you can guess why I call it the thermosphere, because it gets hot. Why does it get hot? It gets hot because it's absorbing X-rays and high energy UV radiation from the sun. And what it's doing is taking these X-rays and this high energy ultraviolet light, which is known as ionizing radiation, and it's ionizing oxygen atoms and it's ionizing nitrogen atoms. So what we find is in this layer of the atmosphere, we're producing uh, O2 ions, and we're producing NO ions. And so there's quite a bit of um, ionic particles drifting around in this area. So it's also called the ionosphere. So some textbooks, instead of calling it the thermosphere, some will call it the ionosphere. And it's just because this is where high energy light from the sun is ionizing particles of the atmosphere and basically converting them into ions. So we find a lot of ions up there. Now, one thing that's interesting is these ions have a tendency to interact with charged particles streaming at the Earth from the sun. So the sun gives off a constant stream of particles, charged particles, protons, electrons, and ions fly out of the sun. The ones at the surface are the convection of the surface is sending them so fast that they achieve what's escape velocity for the sun and they fly away from the sun. So here's the sun. There's a constant flow of atoms away from it. Well, when those, not atoms, I'm sorry, charged particles, when those charged particles interact with Earth's ionosphere, it lights up, making these beautiful patterns. But these are only seen near the north and south magnetic poles. We don't see them, say, this far south of the pole. And here's why. Here's the sun, here's the solar wind. These are charged particles that have escaped the sun because they're going fast enough. And what happens is, and just note this is not to scale, here's Earth's magnetic field, which, as we said before, is produced by the spinning currents inside the liquid outer core. Well, what happens is these particles are deflected because they have a magnetic field about them. So when you take AP Physics 2, you will learn that if you move a charged particle, you make a magnetic field. And a magnetic field can make a charged particle move. So what happens is these moving charged particles encounter this magnetic field, and they bend at a right angle to it. And so instead of going straight at the Earth, they come in this way. And when they hit the ionosphere, they lose energy and cause it to light up in these beautiful displays. And then we have the exosphere. Now the exosphere is just the very upper part of the atmosphere. And what's interesting about it first is the boundary with outer space. Atoms from here get scraped away by the solar wind and leave Earth forever. And the air is so rarefied, that means so far apart, that the atoms almost never come into contact with each other. So what happens is they just go in these ballistic trajectories. So they're like ballistic missiles. They just kind of skip around from one part of the atmosphere to the next, just drifting through space, but they don't have quite enough velocity to escape from us. So they just go up and come back down, kind of like I showed you in that first picture with the moon. So those are the different layers of the atmosphere. Oh, I guess we should just look at this. Okay, so here is a temperature graph you should become familiar with. You will see this on the test. Basically, we're just going to go from 0 altitude to, say, maybe often they go to, say, 200 kilometers, although keep in mind the exosphere goes considerably above that. So what we find is this. In the troposphere, and this is in Celsius, it could be in kelvins, you should be used to either one, same pattern emerges. We start off around 20-ish degrees at the surface, and it gets colder and colder and colder until we get to the tropopause, and then it gets warmer and warmer and warmer as we go to the stratosphere. Then we get to the stratopause. Then it gets colder and colder until we get the coldest temperature in the atmosphere in the top of the mesosphere, and then we have the mesopause, and then we start gaining temperature, and then the hottest part of the atmosphere is in the upper part of the thermosphere or ionosphere, and beyond that we have the exosphere. Okay, so that was the layers of the atmosphere. Thanks for watching. Hope this sticks with you.